I would like to thank the workshop organizers for the invitation to present some of my group's latest research to all of you here today. I'll be discussing some of our latest results on heterogeneous 3-5 silicon quantum photonics. My name is Galan Moody. I'm an assistant professor in the Electrical and Computer Engineering Department at the University of California in Santa Barbara. I'm also a Thrust co-lead on an NSF-funded center called the Quantum Foundry. If you're interested in learning a little bit more about some of the other projects that I have going on in my research group, as well as some of the efforts that we have going on in the Quantum Foundry, you're welcome to visit my group's website listed here, as well as get in touch with me through email. The research activities in my group are divided into three complementary areas. The first is turnkey quantum light sources. We work on designing, fabricating, and testing entangled photon pair source arrays, as well as arrays of single quantum emitters. And then we're also interested in the integration of 3-5 tunable lasers with these sources. We also work on nonlinear photonics for quantum frequency conversion, and so converting single or entangled photons across a very broad spectrum spanning the visible to telecom wavelengths. And lastly, we also work on large-scale quantum photonic integrated circuits to achieve all-on-chip functionality for various applications, primarily in computing and communications or chip-to-chip teleportation. So we focus on quantum photonic integrated circuits. An illustration here shows different applications, for example, quantum logic gates, circuits for boson sampling, and circuits for chip-to-chip teleportation. An important requirement for all of these is that we need programmable photonic integrated circuits that comprise low loss, passive, and active components. Some of the design constraints that we work with are that we operate at 1550 nanometers for low loss photonics and minimal 2-photon absorption in our material systems, less than 3 dB loss end-to-end from source to either detector or grating couplers to fiber, and then greater than 80 dB of rejection or isolation of the quantum light from the pumps. Other components that we'd like to integrate on chip include on-chip single photon detectors, high-speed modulators or switches, on-chip lasers for pumping, and then microelectronic controllers to then control all the different elements. And so if we look at the building blocks for quantum photonic integrated circuit chips, then there's a number of components that we need to get on chip. On the left, I show here a quantum resource. This can be single photon sources, entangled photon sources, or methods for generating cluster or graph states. And then we need to be able to perform single qubit or 2-qubit gates. We possibly need memory on chip, and then also either detectors on chip for Bell state measurements or efficient chip-to-fiber coupling. And so my group works on several of these different components. So on the left, I show some examples of entangled photon pair sources. In the middle here are low-loss tunable Mach center interferometers and tunable high-quality factor filters. And then on the right are waveguide integrated superconducting nanowire single photon detectors with really high detection efficiency and really low dark counts. And we also work on designing new chip-to-fiber couplers. And so in this talk, I'll focus on our recent results on the development of entangled photon pair sources on chip that are ultra bright and ultra efficient. At the end of this talk, I'll also discuss a little bit of our preliminary results on tunable low loss interferometers, as well as detectors on chip and lasers on chip as well. And so there are three primary methods for generating entangled photon pairs or heralded single photons on chip at room temperature. And they all involve nonlinear photonics. So either using nonlinear waveguides, for example, shown here, etched lithium niobate, or nonlinear spiral waveguides to increase the interaction length, or microring resonators in highly nonlinear materials. Each of these processes involve nonlinear photonics. And so through Chi2, for example, you can convert a pump photon into a signal photon and an idler photon using spontaneous parametric down conversion, or through Chi3 processes with spontaneous four-wave mixing, you can convert 2 pump photons into a signal photon and an idler photon. And so I guess the key question is, which material platform should we use? There's a lot of different materials that have been developed and investigated for these types of processes. I won't go into a large amount of detail of these different materials, but I did just want to point out a couple distinguishing features of the material that we use. So I work primarily in 3-5 materials, and so we've developed a new platform that I'll discuss in the next few slides using aluminum gallium arsenide and gallium arsenide on insulator. And I'd like to point out a few interesting features of this material. It has one of the highest Chi2 nonlinearities, the highest Chi3 nonlinearity. And recently we've developed this platform to have really low loss, and so we can achieve more than 1 million quality factor in micro rings in these materials, corresponding to less than 0.2 dB per centimeter. Has a high refractive index for tight modal confinement, and importantly, it has a large band gap, or at least a large enough band gap, such that at 1550, then we can pretty much rule out any sort of two-photon absorption as a loss mechanism in these materials. And so let's just walk through a few of the details on what our AlGas on insulator platform looks like. We take high-quality epi-grown AlGas and bond it to silica, and then we deposit a hard mask, and through optical lithography and passivation, then we can create a really nice AlGas waveguide with silica encapsulation. So here's a mode profile of an example of what some of our resonators and waveguides look like. And a really nice aspect of this platform is that we can achieve anomalous dispersion, which allows us to achieve quasi-phase matching to improve the conversion for our four-wave mixing processes in these materials. An important development on this platform is using a resist reflow process to improve the sidewall roughness of our waveguides and our resonators. So I show here on the left, for example, if we don't do any sort of resist reflow, then we get fairly rough AlGas waveguide sidewalls. With a resist reflow, then we can really improve that surface roughness, create very nice smooth surfaces, really high quality microring resonators. And that's really important because considering the pair generation rate from the four-wave mixing process in these microring resonators, that's proportional to the nonlinearity squared, the quality factor cubed, and then the inverse of the radius squared. And so by improving the quality factor, we can get dramatic improvements in the pair generation rate. And so on the top left, I show an illustration of what our microring resonator looks like in the spontaneous four-wave mixing process. Two pump photons are coupled into the waveguide and then into the microring resonator. Through the four-wave mixing process, they're converted into a signal photon and an idler photon. On the top right is an image of what our microring resonators look like, and I show an SEM image here with the AlGas encapsulated by silica. On the bottom left is a transmission spectrum of one of our resonators. As you can see, each one of these lines corresponds to a mode in the resonator. And so we pump at this wavelength here, for example, and if we zoom in on that on the right here, we can fit that to show that for this particular mode, it has quality factor greater than 1 million. And then through the four-wave mixing process, then pump photons are converted into signal and idler photons that appear at these adjacent sidebands. And what we do is off-chip, we couple the signal and idler photons into tunable filters to filter out everything but just the signal photons or the idler photons at the second adjacent sidebands to help suppress the strong pump field. So I'd like to walk you briefly through the setup that we use to measure entanglement from our sources. We start with a tunable CW laser diode tuned near 1550 nanometers with some polarization control and sideband suppression. We couple that on chip to pump our microring resonator, and then the chip is temperature stabilized. And then we couple the residual pump, the signal and the idler photons off chip into a polarization maintaining fiber. And then we send that through a Mach Center interferometer with a tunable phase shifter. We couple about 10% of the pump light and then detect that pump light to use to feed back and stabilize our interferometer. And then we take the remaining pump signal and idler, we send it through a filter to reject the pump light, and then we split the signal and the idler into a signal channel and an idler channel, and then we detect those photons with superconducting nanowire single photon detectors, followed by coincidence counting. And so to characterize our source, we first measure the signal and idler raw count rate as a function of the on-chip power, and so I show that here. And then we also measure the on-chip pair generation rate as a function of the on-chip power, and it increases quadratically as expected. And we calculate the on-chip pair generation rate by carefully calibrating and quantifying all of the losses in our optical setup. And then what we can also do is use this data to figure out what is the coincidence to accidental ratio as a function of the on-chip pair generation rate. So then we can see that for generation rates on the order of about 1 megahertz on chip, then we can get coincidence to accidental ratios of a few thousand. And so fitting this data here for the on-chip pair generation rate, then we get a generation rate of about 20 billion pairs per second per milliwatt squared. We've also measured the heralded single photon purity at about 1 megahertz pair generation rates, and that corresponds to about 0.004, so really high purity sources. Okay, so now that we've characterized sort of the source itself, now we need to measure time-bit entanglement. So the way to do that is we take our CW pump and then we're propagating that through our nonlinear material. And signal and idler pairs can be created in any of the continuous time bins within the coherence time of our pump. And so what we do then is we pass the signal and idler photons through our Mach center interferometer, basically perform Franzen interferometry. And so what we can do is we add a delay to one of these arms, and that allows us to interfere signal idler pairs generated in early time or a later time within the coherence time of our pump. And so that's exactly what I show here on these two panels right here, measuring the coincidences as a function of the time delay. And you can see that this central peak corresponds to signal and idler photons that went through the short path or the long path and then are coincident in time. And then what we can do is we can measure this peak as a function of the phase, and we can see nice interference between these two paths. And so on the plot here on the right, I show exactly this. I show single count rates, so signal and idler, and on the bottom are the coincidences between them through this interferometer as a function of the phase. And of course, what's really nice about this is we can see as we sweep the phase, then the signal and the idler are not varying as expected, but we see that the coincidences vary with really high visibility. And so if we fit this data, we get a visibility greater than 97%. So let's put these results into a little bit more context and compare the entangled pair brightness of our source to other material platforms. So I plot on this axis here the entangled pair brightness, which is the number of pairs per second per spectral bandwidth shown here in gigahertz as a function of the Chi-3 nonlinearity. And I'd like to point out that I'm showing data here for the brightness for lithium niobate and aluminum nitride. These were done through spontaneous parametric down conversion with Chi-2 nonlinearities, but I'm showing here just for completeness to show their brightness as well. And so what's really nice about the Algas and insulator platform is we've shown that we have about a 500-fold improvement over previous state of the art. And this primarily stems from the fact that the Algas platform has one of the highest nonlinearities, and we've dramatically improved the quality factor of these resonators. And the resonators are quite small, in the order of about 10 to 20 microns in diameter. And so this table provides a comparison of all the different parameters that we've measured for our Algas and insulator platform on the top two lines, and then comparing that to some of these other material platforms for entangled photon pair generation as well. And so I'm not going to go into any extensive detail of this table. I just wanted to point out that we're able to achieve a pretty high pair generation rate while maintaining a high coincidence to accidental ratio, high visibility, and high single photon purity. If you're interested in learning more about this platform and how we fabricate and test these devices, then I'll refer you to this paper that recently came out in PureX Quantum a little earlier this year. And so some key takeaways from these results that I've shown so far is that Algas on insulator is really now an exciting platform for low loss quantum photonics with loss comparable to silicon on insulator and silicon nitride devices designed for quantum photonics. And this is primarily due to the fact that there's a large Chi-3 nonlinearity, small ring radius, and large quality factors. These result in about a 5% conversion efficiency in our devices and about 100 times lower pump power required for the same pair generation rate for some of these other material platforms. And there's some nice prospects for all-on-chip integration. 3.5 materials are naturally compatible with gain detectors, electro-optical modulators, and so forth. Okay, so going back to sort of these building blocks for all-on-chip optical quantum information processing on chip, I just discussed some of our entangled photon pair sources. We also work on other components on chip, including interferometers and detectors. So I just want to quickly kind of go over some of the recent results that we have on these components as well. So beginning with passives and actives for programmable circuits, these mostly revolve around tunable Mach center interferometers. And so I show here, for example, some preliminary results of tunable MZIs that we've made in Algas on insulator. Here, for example, is a third order filter. And if you look at the transmission spectrum of one of these filters, then you can see that we get really nice rejection, greater than 30 dB rejection of our pump with a particular filter that's designed to transmit our signal and idler photons. So we're working on designs of other components as well. These include Bragg filters for additional pump rejection, high quality factor add drop resonators, waveguide crossers, and high-speed electro-optical modulators in this platform. We've also done some extensive work with collaborators for on-chip single photon superconducting nanowire detectors. And it's really important to detect every photon. So that's why we want the detectors on chip. So we've worked with tungsten silicide and niobium nitride SNSPDs integrated on both silicon on insulator and AlGas and gas. Some recent results that have come out of various collaborations include the record sub 3 picosecond jitter timing resolution in detectors. And then with tungsten silicide on SOI and 3.5s, we can achieve about sort of sub 70 picosecond timing resolution on waveguide integrated detectors, really high internal quantum efficiency, pretty high detection rates, and really low dark count rates. So for example, we've measured fewer than 1 dark count in 15 minutes. So to learn a little bit more about our detector integration, you can look at a few different references from the past few years I show here. And then we're also interested in improving the detection rate and jitter with ultra compact cavity integrated SNSPDs. So here's a couple of examples by Vals Willer's group. And if you want to learn a little bit more about that, then you can see this archive article that's a roadmap on integrated quantum photonics with many excellent contributions from different authors in this community. Okay, and lastly, I wanted to show some very preliminary results on some new chips that we've been designing and we're getting ready to start testing, integrating 3.5 tunable lasers with silicon Entangled-Photon-Pair sources. And so we have spiral waveguides here, which generate entangled photon pairs. And then we have our tunable laser here with greater than 10 dB of power, a dBm of power on chip, greater than 40 nanometers of tunability, and fairly narrow line widths. And so in the coming month or so, then we'll be working on demonstrating sort of this turnkey Bell state generator with these chips. And this work was inspired by some very nice work done here at Bristol by Silverstone in this reference here. Okay, so to summarize, we've worked in the past couple of years to develop low-loss 3.5 and 3.5 on silicon programmable photonic technologies for information processing on chip and communications. I'd like to acknowledge everyone in my group has been working on various projects. Their pictures are all shown here. We also work extensively with the Bowers group here at UCSB with many excellent postdocs, students, and staff scientists. I'd also like to point out that we have openings for graduate students and postdocs in our group and in this collaboration. So if you're interested, please don't hesitate to get in touch with me at this email address here. There are several nice fellowship opportunities as well. We have what's called an E-Wings Fellowship for postdocs. You can look at this link here or just email me and I can give you some more info. The deadline is upcoming in a few weeks. And then every year we also have a Quantum Foundry Fellowship competition for graduate students. That's usually at the end of the year, and you can contact me as well if you're interested. So with that said, I'd like to thank you all for your attention, and don't hesitate to get in touch if you want to learn a little bit more about what we're doing here at UCSB.